Hi everybody. The purpose of this video is to help explain how to implement test 19, which is this is test 19 of the quantum computing course engineering 596. And so here you see lecture 19 and test 19 is as follows. The students are asked to find a circuit that implements the transformation shown right here. And so that's what I would like to discuss, to show exactly how to do this on the IBM quantum computer. And this, I don't think that this video will take very long, but I will admit that some of this may be a little bit tedious because I plan to try to pretty much dot every I and cross every T to make sure that everything is clear here. So the first thing I want to do, I already have the quantum computing website open, and I am opening a new lab file here, and I think it's very useful to have some of the code from chapter 6 available. So I'm going to go to our GitHub site, which has all the code from the book, from the textbook for Engineering 596. And I want to copy this first bit of code. I'll run that and then go back to GitHub and copy this second bit of code. And then back again to the quantum computer, and I will paste that in and run that. And then I have some work here I've done previously, and I'm not going to explain all the details of it right now. Just want to copy some of the code. Now this is back to the code that we were working on right here, and you can see the code that we got from GitHub. That's the that little bit there. And so now I am going to paste in this, and I want to delete these two lines. And what I'm going to claim is that this is the code to implement the circuit for test 19. And to give you an idea of what that looks like, there is what I'm claiming is the solution. But to prove to you that this is the solution is going to take just a few minutes, and I have to make a few preliminary remarks first before my explanation will make sense. So the first thing I want to do is to explain that everything on the quantum computing website, all of the circuits are really upside down from what we have in our textbook and what you see in many textbooks. And I will explain, the best way to explain this, I think, is just by giving an example. So, let me look at this extremely simple circuit here. And we'll look and see what it looks like. You can see that this is just about as simple as a circuit can be. We have an X gate on the Q0 qubit, and we have no gates at all on the Q1 qubit. Now, if you were reading this in the way that we have talked about in the lecture for Engineering 596, and in the way that is shown in the textbook for Engineering 596, and also in the way that you see in many other books as well, you would think that this qubit is the qubit 10. But let's check and see. So we'll say QSphere and you see that the qubit is 0, 1, the state is 0, 1 rather than 1, 0. And the reason is that in the quantum computer, you read the states from the bottom up. So that's the first thing to keep in mind when we look at test 19. And we have here, these are all 2 qubit states. And the second of the 2 qubits will be the one on the top line, and the first qubit will actually be on the second line. Okay? So just keep that in mind as we continue with this discussion. Now, the next thing I want to remind you of is let's look, another way that we can look at this situation is to type result. And this is a little bit complicated here, and so I want to make sure you understand exactly what this means. Okay? The first thing to remember is that, we're talking here about a 2 qubit state. And so you might remember that, let's go back first of all to 1 qubit states, okay? The standard basis for 1 qubit states is the 0 qubit and the 1 qubit, or the 0 ket and the 1 ket. That's the standard basis. And you might remember that the vector associated with these, we have a vector 1, 0 associated with the 0 ket, and the vector 0, 1 associated with the 1 ket. Okay, so once again then, for 1 qubit states, we have associated vectors that have 2 elements in them, 2 element vectors. Now, if we had the vector A, B, well, that would represent A times the 0 ket plus B times the 1 ket. And remember that A and B can be complex numbers, okay? So now let's go to the 2-qubit situation. Okay, in 2 qubits, you might remember that the standard basis has actually 4 states. There's the 0-0 state, 0-1, 1-0, and 1-1. That is the standard basis for 2-qubit states. And so, since there are 4 of these, we associate with each one of them a vector having 4 elements. The vector 1, 0, 0, 0 is for the 0, 0 ket. The vector 0, 1, 0, 0 is for the 0, 1 ket. The vector 0, 0, 1, 0 is for the 1, 0 ket. And finally, the vector 0, 0, 0, 1 is for the 1, 1 ket. Okay, so let me say that one more time a little more quickly. The 0, 0 ket is 1, 0, 0, 0. The 0, 1 ket is 0, 1, 0, 0. The 1, 0 ket is 0, 0, 1, 0. And finally, the 1, 1 ket is 0, 0, 0, 1. Okay, and so again, if you had a linear combination of those 4 kets, you might have the vector A, B, C, D, which would represent A times 0, 0, plus B times 0, 1, plus C times 1, 0, plus D times 1, 1. And once again, A, B, C, and D are all complex numbers. So all of them have a real and imaginary part. So altogether, we're talking about 8 numbers here. Okay, now this array here is showing you those 8 numbers. We have 0 and then 0j. So this is the complex number, 2 numbers here, or you can think of it as one complex number, but this is the coefficient of 1, 0, 0, 0. This is the coefficient of 0, 1, 0, 0. This is the coefficient of 0, 0, 1, 0. And this is the coefficient of 0, 0, 0, 1. So this result here says that all the coefficients are 0 except for the coefficient 1 plus 0j, which of course is just 1. So we just have 1. This is basically 0, 1, 0, 0, which is exactly the vector we said that was associated with the 0, 1 ket. So this makes perfectly good sense. And just to do another example, to make sure that this makes perfectly good sense to you, let's do another example. And this time, instead of putting the X gate on the top qubit, we will put it on the qubit on the second line. Now, before I do this, I encourage you to think about what the result will be, and then we'll look at it together. Now, just in case you're a little bit hazy on what we're doing here, as I said here, this time we have the X gate on the second line rather than on the top line. And so keeping in mind that we read the states from the bottom to the top, this should give us 1, 0. So let's check QSphere and see if that's correct. And indeed it is 1, 0. And you can notice here the phase is 0 because it's positive 1, 0. And let's now check the result. And this should give us an array once again. And all the numbers in the array should be 0, except for the number in the third entry, and that should be 1 plus 0j. So let's see if that turns out to be right. And sure enough, the first number is 0, the second number is 0, the last number is 0, but the third number is indeed 1. So I think that all of this should be pretty clear to you by now. But now I want to show you something, and this is actually the reason that it took me a long time to discover that the the original circuit that I had for this problem was correct, but I thought it was wrong for quite a while, and I'll show you why. Okay, so let me demonstrate that point now. Okay, so I'm going to make another circuit here. And just run that. And let's see what it looks like. Okay. So let's think about this for a moment. We see that on the first qubit, again, remember we're reading from the bottom to the top. So the first qubit, there's no gates at all. It just remains at 0. But the second qubit, the one at the top, okay, it gets flipped there, and we just found out that when you flip it, that gives you a qubit of 1. And now we apply the Hadamard gate. And we know that the way that the Hadamard gate acts on the 1 qubit is to yield 1 over square root of 2, 0, minus 1 over square root of 2, 1. So, keeping in mind that the first qubit is 0, we should have 0, 0, and 0, 1. So let's look at QSphere and see what it tells us. When we look at QSphere, at first it looks like things are good here. We have 0, 0, and 0, 1. The two circles here are of the same size, so that tells us that the coefficient of each one has the same magnitude. And of course, remember up here, we said that the Hadamard gate acting on 1 ket is 1 over square root of 2, 0, minus 1 over square root of 2, 1. So we have the 1 over square root of 2 in each case, and so it looks like that makes sense. So everything looks good, but now let's think a little more carefully about this. Okay, if we have 0 for the first ket, the first qubit. If we have 0 for the first qubit, and the second qubit is 1 over square root of 2, 0, minus 1 over square root of 2, 1, then overall what we should have is 1 over square root of 2 times the 0, 0 state, or 0, 0 ket. 1 over square root of 2 times the 0, 0 ket, minus 1 over square root of 2 times the 0, 1 ket. Let me say that one more time. It should be 1 over square root of 2 times the 0, 0 ket, minus 1 over square root of 2 times the 0, 1 ket. But now look down here at QSphere, and notice that we have a red color here for 0, 1, which means 0 phase, a positive number, and we have green, so we have 180 degrees for 0, 0. So this is depicting the answer as 1 over square root of 2, 0, 1, minus 1 over square root of 2, 0, 0, instead of what we think it should be, which is 1 over square root of 2, 0, 0, minus 1 over square root of 2, 0, 1. And so that is curious, and so the way we can resolve that, let's look in result and see what's going on. And notice that this looks exactly like what we would have predicted. Here we have 1 over square root of 2 in the first entry, so that's 1 over square root of 2 times 0, 0, and it excuse me. Sorry about that. So we have 1 over square root of 2 in the first entry, which represents that 1 over square root of 2, 0, 0. And then we have a minus 1 over square root of 2. You can see the minus side there. Minus 1 over square root of 2 in the second entry, which is minus 1 over square root of 2, 0, 1. So the prediction that we made up here was indeed correct. We do understand how the Hadamard gate is working properly, but QSphere is not giving us the correct result. And as I said, that was something that slowed me down quite a bit. I thought that when I ran my code, I thought that it was incorrect because I was just looking at the results as they were depicted on QSphere, and unfortunately I see that QSphere doesn't seem to always be reliable. So now what I want to do is to demonstrate to you the code that I think is correct for test 19, and we'll see how it works. Okay, so let's see what this circuit really looks like. Oh, sorry, I didn't. Everything to the right is the circuit, and this would have been giving an input state of 1, 1, but I want to start with 0, 0, so let me do this again. And I'll take away that and that. And now run it and say IMG and run that. So there's our circuit. I claim that that is the circuit for test 19. Now, if you will look at that carefully and compare it to, well, okay, what I have right here. Okay, here I have, it's not extremely neat, but you can see what's going on. This is what, if we use the techniques of lecture 19, we would conclude that this is the circuit. Now, notice that this is a C0 gate where, well, actually, first of all, let me say that everything here has been, you should think of it as being flipped upside down here. So, for instance, the easiest way to see that is you see that the H here, the control qubit is on the top line here, and what's being controlled is on the second line. But if you compare that to what we have in OneNote, the H, which is U tilde, is up here on the top line. So everything is flipped. Keep that in mind. And another thing to say is that why is U tilde equal to H? Well, we see that U tilde of 0 is 1 over square root of 2, 0, plus 1 over square root of 2, 1. And U tilde of 1 is 1 over square root of 2, 0, minus 1 over square root of 2, 1. And that's exactly the same way that the H gate acts. And so that's why we can substitute H for U tilde. So if we take into account that U tilde is equal to H, and then we turn this upside down, then I think you will agree at least with this part, the very middle of the circuit here in the on the quantum computer, or actually the quantum simulator. Okay, but this group of 3 elements here, notice that this is equal to, is identical to this, but it doesn't look like what we have in OneNote. Now keep in mind, you know, one reason for the difference is that this should be flipped upside down, but even if it's flipped upside down, we just have one thing here as opposed to 3 things in the circuit. And the reason is that this is a controlled NOT gate that gets activated when the control bit is equal to 0. And as far as I can tell, the quantum computer does not have controlled gates that can be controlled in that way. And so what I've done here is I've used the fact that this, you see this controlled NOT gate here is controlled when the top qubit is equal to 0, it flips the second one. And the way that you can obtain that from the ordinary C0 gate is to just do this. And so with these 3 elements, I can produce this. And if you really want to prove that those are equivalent, you need to put in each of the possibilities to make sure, you know, that is 0, 0, 0, 1, 1, 0, and 1, 1. But you would see that in each case, these 3 gates hooked together in this way, or connected together in this way, would act like this. So that explains what I'm doing here and here. But it doesn't verify that this circuit is correct. That's my job now. And so let me go back to OneNote. And what we want to do now is to verify that this code, this circuit will give this behavior right here. Okay? When we put in 0, 0, we will obtain 1 over square root of 2, 0, 0 plus 1 over square root of 2, 1, 1. When we put in 0, 1, we will get 0, 1. When we put in 1, 0, we will get 1, 0. And when we put in 1, 1, we will get 1 over square root of 2, 0, 0 minus 1 over square root of 2, 1, 1. So let's check and see. Okay, so here we've already put, you see that this is the case putting in 0, 0. And so let's see. Now, again, we think that QSphere is possibly, well, we've seen it is sometimes unreliable, but I will still, in each case, I'll look at the results both as they are shown in QSphere and as they are shown with the result listing. Okay, so QSphere. And notice that the circles are the same size, so the magnitudes are the same, and both of these are red, so both of them are positive. So this actually agrees with what we expect. 1 over square root of 2, 0, 0, plus 1 over square root of 2, 1, 1. And let's just make sure that that's what the result will tell us as well. And we see that we have 1 over square root of 2 in the first entry, and 1 over square root of 2 in the last entry, and 0 for the other 2 entries. So sure enough, this is 1 over square root of 2, 0, 0, plus 1 over square root of 2, 1, 1. So far, so good. Now, what we'll do is, instead of doing, actually we'll do 0, 1 next. Okay, so let's run this. And let's do IMG just to make sure we understand what's going on. And so you see that remembering that we read from the bottom to the top. So this is 0, 1 over here. Everything to the left of the barrier is preparing the qubit, and then everything to the right of the barrier is our circuit, which does not change. So this is 0, 1. And remember that this should give us 0, 1. Let's see, let's remember. 0, 1 should give us 0, 1. So let's see if that is indeed what we will get. Again, we can look at the results from QSphere. And that does indeed tell us that it's a positive 0, 1. You see it's red, so that's a 0 phase. So it says it's positive 0, 1. But now let's check with the result. And sure enough, here we see a 0 for our first coefficient, 1 for our second coefficient, 0 for the third coefficient, and 0 for the fourth coefficient. So this is 1 in the second coefficient, which is the 0, 1 kept. So that looks good. Now let's try 1, 0. Okay, you can see, once again, remembering we read from the bottom up. So this is 1, 0, and 1, 0 should go to 1, 0. So let's see if indeed that's what we obtained here. We can again check with QSphere. So far, QSphere has given us correct results on everything. And once again, QSphere seems to be giving us the correct result. Is 1, 0, it's red, so that's positive. But let's check with the result. And we see 0 for the first coefficient, 0 for the second coefficient, 1 for the third coefficient, and 0 for the fourth coefficient. So that is indeed, since all the coefficients are essentially 0 except for the third one, which is 1, that corresponds to the 1, 0 ket. And so now we have just one more to go. Let's run it. And then ENGR. So now you can see that we are indeed putting in the 1, 1 ket into our circuit. And remember that 1, 1 should be giving us a result of 1 over square root of 2, 0, 0 minus 1 over square root of 2, 1, 1. Okay, so going back to the quantum computer, if we look at QSphere, you see that this is giving us the two circles here are the same size, so the coefficients are the same magnitude, which would, in this case, since it's 2, would be 1 over square root of 2. But notice that this one is positive and this one is negative. So this would indicate that we are getting 1 over square root of 2, 1, 1 minus 1 over square root of 2, 0, 0. Which is not the result that we want. But if we look at result, remember we've already seen that QSphere gave us an incorrect answer before, and so we suspect that this is incorrect again. But let's check and see, and sure enough, you will see here we have a positive 1 over square root of 2 in the first entry, a negative 1 over square root of 2 in the last entry, and the other two entries are 0. So this is 1 over square root of 2, 0, 0, minus 1 over square root of 2, 1, 1. And so, so this is the correct circuit right here. Everything there to the right of the barrier is the correct circuit for this problem. And this everything there, well, that's the way that you can produce that circuit, and you vary these first two lines to get the different inputs. And that is the solution to test 19 of engineering 596. And just keep in mind that the QSphere application, unfortunately, is not giving reliable results. So that concludes this video, and I hope that that will help you in understanding how to implement circuits on the quantum computer.